if I'm going too fast, you will stop me.
Yes.
Your
so
job.
I'm familiar with the decision theory stuff. I just didn't attend the previous.
Oh, if you, that's good enough.
All right.
So this is a particular approach to making decisions. This is going to be a fairly short talk, less than half an hour if I do it right. Where I'm going to try to convince you there's a real problem, and I have a fix.
All right.
If you don't believe me, you'll complain and let me know what you don't like.
All right.
There's a small price to the fix, which is a more complicated representation,
All right.
but nevertheless. So I'm going to assume then that all of you have seen the basic picture of Savage, where there's a set of states and a set of consequences, and acts or functions from states to consequences. If you haven't seen this, raise your hand because you're going to be confused, and I have to go explain. Okay. And Savage has a representation theorem. What that means is he shows that, so he's assuming an agent has a preference order on acts. Acts are these functions from states to consequences.
Okay.
And if your preference order satisfies certain postulates, axioms of your logician, then you're acting as if you have a probability on states, a single probability, uniquely determined, and a utility function on outcomes, which is unique up to affine transformations. What that means is, if I have a utility function, you can multiply it by 3 and add 5. So an affine transformation says you can multiply it by a real number and add a constant. That doesn't change it. So the only way the two representations can differ is if utility functions are related by an affine transformation. And his theorem is, if your preference order of acts obeys my postulates, you're acting as if you're maximizing expected utility. By which I mean you have this probability function on states, this utility function on outcomes, and you're taking the act that has the highest expected utility. And expected utility here makes sense because to compute the expected utility, you just multiply it of an act. You multiply the probability for each state, multiply the probability of the state times the utility of the outcome you get from that act. So I'm assuming, I'm not writing this down carefully because this is what I'm assuming you knew walking in the door.
Yes.
And if not, speak up, raise your hand, commit violence, do something.
I mean, I'm kind of a fan of imprecise probabilities, so there's presumably some aspect of this proof where I would be like, I disagree with that particular thing.
That's the core of the talk. So stay tuned. I think Savage's theorem is beautiful, but I am not a big fan of always using probability to represent things. And here's the problem. Suppose I have a coin, and I have no clue of the probability of heads. Now, what would a Bayesian? I said, well, symmetry. I have no information. I'm going to take the probability of heads to be a half. I said, where did that come from? You had no clue, and all of a sudden you're telling me the probability of heads is a half. Now, the typical Bayesian answer would be, just let me collect some data, and I'll figure out the right answer pretty soon, which is true. Yeah.
I'd say that the fact that it's a coin at all is smuggling in a large amount of prior data. And if you really want to say that you have absolutely no idea, just be like, this is a black box with completely mysterious
I agree with you, but let me not get to that level.
Yeah.
Now, you might think, okay, pointy-headed theorist, he's worried about these things. Why should I care? Now suppose you're Uber. You have a real application. You're trying to figure out, how many drivers to get for a certain area. Or you're a doctor and you're trying to figure out how to treat a patient. Now, you typically, the doctor part I know was I talked to a doctor. He said, yes, this is the kind of thing that happens all the time. He said, well, he worked in one town, and so he knows the distribution of patients and the kind of diseases they're likely to have in town A. But then he was moved to town B. Now, it's not true that he had no clue of the distribution, but he sure felt like he didn't have much of a clue of the distribution, and he saw no reason to believe it was like town A. Or think Uber, where you're trying to figure out, at 5 o'clock, how many people, what's the distribution of how many people are likely to want a ride at 5 o'clock. Now again, has tons of data. And they might very well have data from somewhat similar towns, or locales, or whatever, and they want to use that, but they don't know about this particular town. And I would argue that Uber wants to, at the beginning, and certainly the doctor wants to, but he agreed. He was really uncomfortable about taking the data from town A and applying it to town B, or even averaging the data over towns A1, A2, and A3, because he just didn't know which was right. So I'm looking for a method that allows me to take seriously that at the beginning I'm to some extent clueless. I'm not going to define clueless, but think I really don't know exactly what the distribution is. And I get less and less clueless, more and more clueful, as I learn more and more about the distribution. And if I'm willing to assume there's a true distribution that underlies the data, which we can debate, let's suppose, then eventually, with probability 1 technically, I'm going to converge to the true distribution. That's just the way things work. So I'm really interested in that interval from the beginning, where I'm pretty clueless, to the point where I feel I have a pretty good understanding of the distribution. Because, I'm Uber, I've been in this town now for a month, I have a ton of data after a month, and I have a really damn good understanding of the distribution. Maybe not perfect, maybe certain holidays that haven't happened yet, I don't know how things are going to work, so again, not perfect. Likewise the doctor, but you feel like you have a pretty good understanding. So I want to know how to make decisions in the interval from the beginning, when I'm clueless, to, let me say the end, but there's no real end, when I have a much better idea of what's going on. Yeah.
Is there some aspect of it that isn't captured by the classical phenomenon where adding a new data point to 4 data points produces a bigger change than adding a new data point to 1,000 data points?
That phenomenon is certainly relevant, that at the beginning you only have, let's say, 4 data points. You learn the 5th one, your distribution is going to change a lot.
Yep.
But we're going to take it up all that.
All right.
So here's the idea. Now, doing this comes at a price. So for one thing, I'm going to take what you'll call imprecise probabilities. Rather than having a single probability, I'm going to have a set of probabilities. And the second feature is each probability is going to come with a weight. You can think of it as a second order probability, but it will be a number between 0 and 1. But I'm going to represent cluelessness by all distributions have a weight of 1. So it's not exactly a probability.
Okay.
But nevertheless. So the next step I need you to know, so that's by way of background. How many people know about regret? It's okay if the answer is no, I just want, how many people, better yet, how many people don't know about regret and how to calculate regret? Okay, so let me do a brief review for all of you who are too shy to raise your hands. To calculate the regret of an act, what you have to do is figure out, it's the regret of an act in a particular state, the same states we've been talking about here, an act is a function for states outcomes. So to calculate the regret of an act in state S, you figure out the utility of the act in state S, just like we would for maximize and inspect utility. And you figure out the utility of the best act in state S. Like if you had an oracle to tell you, if you're in state S, that's what you should do. Bet on that horse. That's the one that's going to win. The difference between the utility of the best act and the utility of the act you actually perform is the regret of the act you perform in that state. So intuitively it's the, oh shit, I wish I had done that. And regret is measuring how badly you feel for not having done the right thing, and instead you did whatever you did. Does that make sense? Now, you can also compute, if you have a problem in states, expected regret. Because again, each state you have a regret, I just told you how to compute it. Multiply the regret by the probability, sum over all states, you get the expected regret. Now note in each state, you're going to be comparing possibly to a different act, because you're performing a particular act at 1, but when I'm computing the regret in state S, I look at the best act in state S, and that's what I'm comparing myself to. When I'm looking at S prime, I look at the best act in S prime, which could be a totally different act. And that's what I'm comparing myself to. Okay, here's the amazing theory, there's a really easy proof, but I find it really surprising. If your decision rule is to maximize expected utility, so you order acts by saying, I prefer act A1 if it has a higher expected utility than act A2, that's what's recommended. That's exactly the same ordering as ordering acts by minimizing expected regret. So if you preferred act A1 because it had a higher expected utility than A2, you should also prefer A1 because it has lower expected regret than A2. Right? You want higher expected utility, but lower regret because you don't want to be so sad. Right? So that's the theory. And you know, I'll find I can prove the theory, it's not hard, but let's say you accept it. Okay. Okay, that's for a single distribution. So for a single distribution, whether you're an expected utility maximizer or an expected regret minimizer, doesn't matter. You're going to make the same decision. Not only are you going to make the same single decision, you're going to have the same ordering on acts. Okay, are we together? I'm getting there, I'm almost there. Now, let's go back to what I said, your representation now is not a single distribution, but it's a set of distributions. Moreover, it has the added complexity, these distribution comes with a weight, and the weight is normalized to be between 0 and 1. But the weights could all be 1. I'm going to insist that at least one distribution has weight 1, so they can't all be 0. Okay, that's just a technical requirement. Okay, so my decision rule is going to be minimize weighted expected regret, let me explain. For each distribution in your set, compute the expected regret and multiply it by the weight. Why? Well, the weight is supposed to be a measure of how confident you are that this is the truth distribution. So if the distribution has low weight, you don't want to take it seriously. That's the whole point, low weight. So by multiplying the expected regret by the weight, this is a way of capturing that you're not taking it seriously, right? If it had weight 1, you would take it totally seriously. If it had weight 0, well, multiplying by 0 gives you 0, so you basically don't count it at all. So for each distribution, you compute the weighted expected regret, right? You can compute the expected regret, just multiply probability terms for each state that there's regret at that state, multiply it by the weight, and choose the act. So for each act, you can compute its weighted expected regret. Right? Are we together? I'm almost done here, so if you have any questions, you absolutely should stop me. I do not take any offense at being stopped.
So I assume you sum up the weights instead of taking like a min or a max over them?
No,
I
I
mean,
take
you
the
sum
worst
up
case.
the...
I take, for each distribution, I take the weighted expected regret for that distribution.
And now you have a set of...
Now I have for each distribution, I have an associated weighted expected regret.
Yes.
I choose the act that minimizes, whose worst case weighted expected regret is best. It's like a max min.
Yep. All right.
Does that make sense? So for each act, I can compute the worst case expected regret, because for each distribution, I look at the expected regret. So the worst case over distributions. You have a continuity, but there actually is a worst case. You don't just approach a limit. But if you approach the limit, take the limit. I don't care.
Yeah.
As a technical matter, you do approach a limit. I mean, you take on the limit. There's some distribution where you take on the limit. If you take, I mean.
Yeah.
So again, for each act, for each distribution, you look at the weighted expected regret of that distribution for that act, and take the worst case, and choose the act that has the best worst case expected regret. Now,
so what happens to the weight that is associated with each probability distribution?
I'm using that to compute the weighted expected regret.
Oh, okay, I see.
Right. So for each probability, I don't just take the expected regret. I take the weighted expected regret.
Right.
That's important.
Yeah.
And we'll see the second why it's really important.
Intersecting.
So I wish I would have taken would have been the same. So then this just falls out and it ends up being, is it just the same as max min that's weighted by these weights?
If it's the case that no matter what you've taken the same action, then yeah, it does look like a max min, but why should it be the same? Again, not following.
Okay, so I have a set of actions.
Right, so for each action you do this computation separately.
Yeah. Sorry, why is it different that yeah, I'm just being slow.
No, it's okay.
Why is it different that you have different actions that you would have wanted to take?
Well, that's, you're trying to decide which action to take.
Yeah.
This is the standard decision tree setup. You have 10 possible actions, which one should you take? Right, so the standard way of doing things is for each one, compute the expected utility, choose the one that has the highest expected utility.
Yeah.
So I'm saying, okay, now, for each one, compute the worst case expected red, and instead of choosing the
Oh, and that's going to be different for different worlds. And then in the different world, my best action in that world would be
well,
different.
the regret will be different in different worlds. The expected red takes all the worlds at once, so you're taking expectation over all these worlds.
Yeah, yeah.
But nevertheless, it makes sense to talk about for each act what is its worst case expected.
Yeah, sorry, I'm there.
expected
I'm
red.
there. Thank you.
Okay. Here's the punchline. Why did I do all this? Why do I want to add weights? Why do I want to complicate my life by having sets of distributions and weights? Okay. Let's take a simple case where you've got a coin. And at the beginning you're clueless. You have no idea what the probability of heads is for that coin. So the way I would model that is saying, okay, you have a set of distributions. Each of them has a weight 1. They're all, as far as I'm concerned, equal good. I have no preference. And they're distributions on the probability of heads. Right? Now you start tossing the coin. Toss it 10 times, you get 7 heads. Toss it 100 times, you get 72 heads. Well, now you're going to want to update the weights. And a standard way of updating the weights is by using maximum likelihood. You're saying, how likely are you to see 72 heads out of 100 if the true probability of heads was 0.3? Well, not terribly likely. So the updated weight, which gets normalized to the highest weight is 1, is start out, everything has a weight of 1, and then update, conditional on your evidence, by using maximum likelihood. So you get a new set, the same set of distributions, but now new weights. Okay. Suppose there's a true distribution generating the data. What do you expect will happen pretty quickly? This is a sanity check to make sure you're following. So I'm going to stop here and wait till I get an answer from somebody.
Approach the distribution.
Sorry?
Your beliefs will approach the true distribution, right?
Exactly. Right? I mean, just using maximum likelihood, like a Bayesian would say, sooner or later you're going to figure out the truth. Well, I agree. Sooner or later, and actually in this case pretty quickly, you're going to figure out the truth that if you just do this process, that you'll find over time, there'll be one distribution whose weight is 1, and then the weights of other distributions will drop off very, very sharply from that distribution. They'll never actually reach 0, but epsilon for very small epsilon, you can make all this precise. So in the end, things look like you have a distribution on a single probability measure, the one that you're converging to. I mean, it's not quite true, but it's good enough. So what is the effect of that on the calculation? Well, remember I told you when you had a single distribution, minimizing expected red is the same as maximizing expected utility. Bottom line.
So at the beginning, you spread out your distribution on actions to be something that all the possibilities are like, it's
Yeah, you're
pretty
much more
decent.
conservative at the beginning.
Yep.
Because intuitively, exactly, you spread out your uncertainty, you're getting everything weight 1, and your actions are going to reflect that. They're going to be much more conservative.
Mm-hmm.
And as you learn the true distribution, you're going to converge to a single distribution, and you're going to converge to being an expected utility maximizer. Now, there's nothing in the rule that says, here, at this point, we flip to expected utility maximization. This all happens automatically. It's the same rule, the rule doesn't change. Right? And everybody can sense? I know you have a question, so I forgot. But the point here is that you start out being clueless. As you get a better and better idea of the true distribution, you're converging to being an expected utility maximizer, to being a good Bayesian. But at the beginning, when you're really clueless, I object to being a good Bayesian. I don't think it's reasonable to act like the probabilities that happen, you have no clue. But I'm totally happy with the Bayesian response of just wait, sooner or later you'll figure things out. You had a question.
Yeah. So I like this idea of having this extra number that weights each of the probability distributions to have the notion of actually being clueless. You talked about over time, as I keep flipping this coin, I keep running maximum likelihood in order to figure out what these extra weights are. And when I hear maximum likelihood, I think, what is the single probability distribution that makes this observation as likely as possible? So that I'm expecting to see a single
The
spike.
right way to think about it here is how likely is for each distribution P? How likely is P to have been the distribution that generates the data that I'm seeing? So what's the probability that I would see the data that I'm seeing if P were the true distribution?
And then normalize that.
Yeah, and the higher the probability, the better the distribution is, the higher weight it gets. Exactly, normalize that.
Oh, do you normalize it, or do you separately for each
Well, I
one say-
normalize it because I'm insisting the weights are an interval 0 1. Yeah, all of our next.
Sorry, so I guess I wasn't quite clear on how, maybe if you could, like, how this was going to not be equivalent to a Bayesian account. Like, I could have a distribution over the bias of the coin, right? Like, I could have, like, and then I would still, I could be spread out over, like, what the bias is. And then it's as if I have these different probabilities that I'm, like,
So
averaging.
if you were
Right,
working
you
with a
could do something
second
never
order
been.
distribution,
Yeah.
and you could deal with some technical problems, for example, as I said, that I could have literally an uncountable number of distributions, because if I talk about what's the probability of the point line's heads, it's some alpha where alpha is between 0 and 1, and it's uncountable. So the set of distributions on which I'm putting a weight is uncountable, but I want to put weight 1 in all of them, that doesn't look like a probability. So modulo the fact that if everything were finite, you could view the weights of second order probabilities, put on a weight.
Would you do everything that's never Bayes in this account in the beginning? Like, was there none that would be
At the
rationalizable or whatever?
beginning, well, again,
Yeah.
so the typical Bayes approach would be to start out with a single distribution, not a
Right.
second order distribution. Absolutely, at the beginning you would do different things. Right, treating the probability of heads as a half is very different from saying I have no clue, in terms of the decision that you're making, in terms of the act that minimizes expected regret. We have a bunch of examples in the paper.
Oh, but I mean, like, you would choose an act. I mean, is there an act that you would choose under this account that a Bayesian would never pick?
Would never
Or-
pick.
Yeah.
Well,
Like, I mean, like, for instance, if you said pick a dominated option, right?
Oh,
Like,
I think I know. That for evasion, the maximum expected utility is always at a single action, or there are actions that tie for the best. Where for rules like this, they can say the optimal move is to play this probability distribution over actions, and nothing representable is just a probability plus utility, maximize expected utility, can endorse a probabilistic mix of actions is the best.
The Bayesian would allow for probabilistic mix of actions, but I'm not sure I understand what it would mean not to do something that Bayesian would do, or make that more precise.
So, I mean, you have some act space, right? Like, some of these actions are ones that couldn't be rationalized by any Bayesian, right? Like, some of them are going to be like, strictly
would I
known.
ever choose
Some of
an
them
act
would be like
for which there isn't some distribution that a Bayesian.
yeah, or even maybe diachronically, where like T1 you would pick one and T2 like no probability
thought
function
about
up that way.
I would guess no. I mean, I would guess you'd always be able to find a distribution that would rationalize it from a Bayesian perspective. Take out with a grain of salt. I haven't thought about it.
Okay.
All of you had a question.
I was just going to address the maximum likelihood. I think you
You expect me to remember the titles of my paper. My co-author is Samantha Leung, Leung. It appeared in the Journal Theory and Decision
Alright.
and the UAI conference, and it probably has words like "way to expect regret" in it somewhere. Although I can't swear to that.
How
If
easy.
you can't find it easily, ping me and I'll
Alright.
look into it.
When did you publish this?
What was
I
the
would
day of
guess
the
about
week?
10 years ago, but my daughter passed me on the head and says, "Dad, you're getting senile." I don't think I'm getting senile, but things like dates of papers and titles of papers, they're gone. I don't think it ever lasted very long. There's a question up here.
Yeah. So you started off by saying that Savage's representation theorem is a thing of beauty, and I agree.
Right.
I'm curious, what would an agent who behaves in this way be representable as?
Oh, we have a representation theory. Funny you should ask. You almost see when they get published in journals like Theory of Decision. But now if you ask me what are the differences between that and Savage, lost in the midst of time that I could recover it. But we definitely have a representation theory. So we played the game the way decision theorists would play the game. I saw a question back there.
Yeah, hey, I'm sorry, I think I arrived late. This is the paper from, like, I think, 2012, weighted expected sets of minimax regret sort of thing, right?
Something like that, yeah.
Yeah, so I think, like, I was looking at this paper a short while ago on the recommendation of Davidov, who
Yeah, he
says-
likes this stuff. I spoke to him about it and he thought that.
Yeah, and I think, like, and I was impressed by the fact that, like, you could come up with a representation theory, like, even with, like, incomplete release, and I think there was, like, some curiosity on whether such a thing could be also done for incomplete references.
What do you mean by incomplete in this case?
Well, where there is, like, there are options where we don't necessarily have yet decided, or don't necessarily know whether we prefer one or the other.
Couldn't that be modeled by a partial order where you have two things that are incomparable? That's the standard way to model incompleteness?
So I think that there's a difference here, which is, so for example, like, you could have two things which are not indifferent, but you just haven't decided whether, like one is better than the other.
That's exactly a partial order on preference hunt, because you don't know if you prefer A to B or B to A. So
Right.
I think you could capture that. But I'm worried that we have like 30 seconds to go.
I'm the next speaker.
That's right.
I'll come back. And I'm the next speaker. I guess you know that. So for this talk, I'm actually going to use. How can I do
You didn't
this?
use the word.
Is there an easy way to get this out of the way without blocking people?
No, I thought there was a slot back here.
Well, yeah, there is sort of kind of.